All right, guys, so let's continue with chapter 24. So we are going to be looking at deriving the equations for the standing waves, and we're going to use a string standing waves or standing waves on a string to derive the equations first, and then we're going to look at standing waves in pipes. So let's say they're going to be in terms of air columns. So standing waves have application both with the strings and with basically which is a transverse waves and longitudinal waves where the air molecules can create sound depending on the standing waves inside some kind of let's say pipe. So we can have a pipe that is open on one end or open at both ends and things like that. Right, so let's look at in terms of first deriving the equations for a string. And let's say we have a string that is fixed at both ends and it has a length L. And in order to generate a wave, so we, let's say we plug it and we let it vibrate. So one of the things we're going to get here is, let's say the idea for the standing wave is that the wave can, let's say, propagate like this, then going to hit the barrier right on the other side, and then it's going to reflect back. It's going to reflect back on itself and generate basically a shape like this, and then just go back and forth between those as we talked about previously. So this is basically what we have for the standing waves, and the standing waves will be, represented in terms of number of antinodes or number of modes, right? So we can kind of look at it in terms of that. So, but again, there's a boundary condition for the waves. So we can say that here's the, let's say we take that as 0 and this one is length L. That means, we can use the, let's say the left side as a reference position and look at where's the position of the first node or the first antinode and second node and so on and so forth. Also the number of antinodes. So in this case, 1, 2, 3, 4, 5, 6, 7. This is basically represented in terms of m equals 7. Or, actually, n equals 7. So our textbook uses n for that. And that represents basically number of shapes or number of antinodes. Okay. So you can write the ends of the string must necessarily be nodes. So that's, the condition that we have. So for the string wave, both ends has to be node because both ends are fixed. So, and we're always going to have one extra node compared to the antinode. So you will see from the, a shape that I will show you in a minute. So, and every time we're considering a node, so a node is a point of contact where there is no oscillation. That means the node is a part of a matter, right? Part of the string that actually not oscillating. So again, so you can see, right, the boundary condition results in the string having a set of normal modes. So that n going to be representing this normal modes of vibration. Each mode has a corresponding frequency. That means going from one shape or one segment or one mode number to another, then we have to have a specific frequency, not just any frequency that we want. So we're going to see that once we set up our first, let's say, a standing wave, and then the next one with two shapes, for example, then cannot just be some random frequency. It has to be actually very closely related to the first frequency that we use to get the first mode. So we will see that. All right, so each mode, you can get the normal mode of oscillation for the string can be described by imposing the requirements that ends be nodes and that the nodes and antinodes are separated by quarter of a wavelength. So we already talked about that. So you can see that, for example, this is the first shape we can have, where you get two nodes and one antinode. So this is a node on each end and a one antinode. That means basically this is the first shape we can have with just one antinode. So we take this mode number, right? So this mode number to be equals to 1, and we represent it with n, and this is always kind of equivalent to let's say the number of antinodes. All right, so also there's a relationship between the length L and the wavelength, because we can see here is that this wave is only representing the half of the wave, wavelength, right? Because let's say this would have been the actual wavelength, and then in this length of L, we have only half of the wavelength when n is equals to 1. So lambda with the subscript 1 represents basically when n is equals to 1. And this is known as a fundamental or the first harmonic. Okay, so the fundamental or the first harmonic is when this mode number n is equals to 1, which means basically number of antinodes is also equals to 1. So we have just one antinode. And in this length L, right, that means on the string, we only get basically shape for the half a wavelength. Okay. All right. So then kind of rearranging this, you can see then, you can see right in 1L, you get only half of the wavelength. That means to get full wavelength, we need basically twice the length of the string for that, because as I said, right? So for that to, generate the one full wave. So that means this is basically that relationship where lambda 1 equals 2 times L, because for the n equals 1, we're only getting the half of the wavelength, distance. So that's why you can see, right, going from a node to an antinode, then this is a quarter of a wavelength distance, because now what we're saying is that distance from one node to another is half a wavelength. That means distance from one node to antinode, or from antinode to a node, right? Always it's a quarter of a wavelength distance. All right, so here then we can generate another segment by increasing frequency. So one of the things we're going to talk about that, right? So by the way, you can see, right, this is F1 over there, which is the frequency, fundamental frequency. So we call that fundamental frequency. And generally one of the things we can use here is to remember that frequency and wavelength and the speed of the wave are related with this equation, right? V is equals to wavelength times frequency. So then technically this frequency 1 is equals to the speed of the wave, right? Divided by the lambda 1. Again, we'll come back to this again, but this is general, equation for the, the fundamental frequency. Again, because this shape represents the fundamental or first harmonic, and this frequency is known as a fundamental frequency. Then we go to the second harmonic. Well, the second harmonic means that we're getting two antinodes, or n equals 2. So n equals 2 means because there are two antinodes, and now we get 3 nodes. And remember, I mentioned, right, nodes are always one more than the antinodes. So 2 antinodes, so n equals 2. And then we can see, right, already here I'm getting the full shape of the wave. So then in this length L, I'm getting the, entire wave. So L equals the same length as the wavelength for this particular second harmonic. Okay. Then by looking at in terms of how we can incorporate this mode number in, this particular equation, we can see that we can rearrange it and basically represent it like this. Lambda n equals 2L over n, or by rearranging, I can say L is equals to n times lambda over 2, where n is equals to 1, 2, 3, 4, and things like that. So that's why you can see, right, when n was 1, the mode number, so then it was like lambda over 2. This is for, well, L doesn't, so let's say this is for the lambda 1 because n was equals to 1. When n, n equals 2, so then 2 times lambda 2 over 2 to cancel out, so then you get lambda 2. And that's exactly what we have here, and so on and so forth. That means you have kind of like this two equation, which is the same equation, or just rearranged two different ways. One representing in terms of lambda, on the left side, one just representing the L being on the left side. But you can see that they are basically same equations. And going from second harmonic to third harmonic, then we are increasing the number of segments or number of antinodes. Which means that n equals 3. Then we can see, right, then L is equals to n times lambda over 2. So if we're considering lambda 3, then this is 3 times lambda 3 over 2, or 3 halves lambda 3. Means that we have to get like 1.5 of the wavelength, right? 3 halves is like 1.5. That means 1.5 waves. That's what we get, right? 1.5 a wave. So this is in terms of one wave, or like, in terms of like one wave, and this is then a half a wave. So then combining together, we get, 3 halves of the wavelength. You can see, right, every time then frequency changes, so does the wavelength, for this particular harmonic. Again, so the first harmonic, or, is the fundamental frequency, right? There's a fundamental. Then we get the second harmonic, and we get a third harmonic, fourth, fifth, and so on and so forth. That means the number for the harmonic represent number of the mode number, right? Or number of, antinodes. So putting everything together, so as I mentioned, right? So you have this equation where a frequency is equals to velocity over the wavelength, but then we just, learn that we can rearrange or represent the wavelength in terms of this L and the number of modes, right? So which is equals to 2L over N. So if I replace this lambda with a 2L over N, then we pretty much get this equation over here for the wavelength. Oh, sorry, for the frequency. So this equation for the frequency of the harmonics. That means it's N times 2L times V, N over 2L times V is the then frequency. So that's why, for example, for when F is, the fundamental, which is, F is 1, then I can say that this is equals to 1 times the velocity over 2L. So it's basically V over 2L. This is the equation for the fundamental frequency. Okay. Now, then if I'm getting this to be specifically a string wave, if you remember, we talked about the string, speed of the string wave can be represented in terms of square root of the tension force. So this is the tension force, not the period. That's why I'm writing as F of t. Then divided by mu. Mu was the mass per length, right? The linear density. So it's mass per length. So those equations then in a way can be plugged into there and represent, or replace the velocity of the wave. So that means, the frequency is equals to N over 2L times square root of, tension force over mu. Okay, so, but here's then one interesting thing I have. So let's say this is so you can say, right, this is the fundamental where the F, N equals 1. So that's basically for the fundamental equation. And then, for example, then the second one, F of 2, is equals to then, remember, is N2L times V, right? Or N2L times square root of F of t over mu. So let me just write V for a second to make it a little bit shorter. So this becomes, for example, 2 times V over 2L, or this is 2 times V over 2L quantity. But if I remember, V over 2L is nothing but my first fundamental frequency, then F of 2 is equals to 2 times F of 1. Same way, F of 3 is equals to 3 times F of 1, right? Then F of 4 is equals to 4 times F of 1. In a way, this means that F of N is equals to N times F1. You can also write that where this is what the F1 is equals to. Velocity divided by 2L. Okay, so let's say going back, for example, here I have this shape, N equals 1. So for example, if I calculate the fundamental frequency in here and then I get, let's say, 200 hertz, that's my fundamental frequency. Then to go from N equals 1 to N equals 2, which is right here, what I need to do, not just choose some random frequency, but specifically frequency that is equals to 2 times F of 1. That means this has to be only at 400 hertz frequency. Then we can see that. Then the next shape, which is third harmonic, cannot just be some random frequency. It has to be F3, which is 3 times F1. That means this is basically 600 hertz. And you can see, right? And then the next one is 800 and so on and so forth. Because what we get here is going from N equals 1 to N equals 2, N equals 3, N equals 4. We need to find a very specific particular frequency, because we talked about that, right? So that the mode number, right, or the modes, right, each mode is represents very a specific type of frequency. It has a characteristic frequency. All right, so then that's what we have. So the frequencies of the remaining normal modes are integer multiples of the fundamental frequency. Frequencies of normal modes that exhibit such an integer multiple relationship form a harmonic series, and the normal modes are called harmonics. Yes, summarizing, so right, a fundamental frequency F1 is the frequency of the first harmonic, then the frequency F of N equals N times F of 1 is the frequency of the 9th harmonic. That means you can, go and look at in terms of whatever frequency we're considering. All right, so I want to for example, show you a simulation to kind of see how this can be worked out. All right, so here I have a standing wave, and this is a string. Let's say we start with the string. So then let's say showing the length L, you can see, right, L is, a half a wavelength, so 0.5 wavelength. And then, this is basically the first harmonic. So you can see, right, this is the first harmonic. So pretty much this is what you get. And obviously, this is very, a small frequency, right? So that's why you can see kind of going back and forth. When the frequency, let's say 100 or 200 hertz, you're not going to be able to see actually, this going back and forth. You just basically see the standing shape. But, this is slow so that you guys can see sort of like what's going on. So now, in order then go from the first harmonic to, let's say, second harmonic, then we basically increase the frequency, and basically in this length L, we then also have in the length equals 1 wavelength, right? So, and which means in a way we're decreasing, wavelength, right? And what we're getting here is basically n equals 2, right? Because you basically get 2 shapes, okay? Then you can go from here to, 3 shapes, and this is basically what the standing wave is. But again, you can assume that it goes back and forth very fast. So you just basically, unfortunately, doesn't, allow us to do that. But more or less, think like this. So this is basically moves back and forth and gives you that shape. And you have now n equals 3. So L equals, 3 halves lambda, or 1.5 times lambda. And you can see, right, you can just continue going and increasing the harmonics. Every time you increase harmonics, frequency is basically, increases as a, integer multiple of the previous frequency, right? Or the fundamental frequency. And the wavelength basically decreases. All right, so so next we can talk about standing waves in air columns. So there's also something that we can use. We have basically some air columns, and we can have then standing waves, generated inside. You can write standing waves can be set up in air columns as the result of the interference between longitudinal sound waves traveling in opposite direction. The phase relationship between the incident and reflected waves depends upon whether the end of the pipe is opened or closed. So remember, the difference here is that string wave is closed at both ends. So you have nodes at both ends. In terms of this, then the string waves in air columns, you can have what we call open, open, or you can have open, close. So for example, this will be like, let's say, an open, open, which is, I don't know, like, let's say one of those musical instruments where there's open at both ends. I don't know, flute maybe, right? And then you have something that is closed. So it's closed at this end, but let's say open at this end over here. So this is then, open, open, or open, closed. And you get completely different, basically, let's say, standing waves inside. And we're going to look at those, in terms of how each one can be set up, how we can calculate the harmonics and things like that, because we can pretty much do the same thing for this. Okay, so you can see, right, that the closed end of the pipe is a displacement node in the standing wave. The wall at this end will not allow longitudinal motion in the air. The reflected wave is 180 degree out of phase with incident wave, and the closed end corresponds with the pressure antinode. It is a point of maximum pressure variation. Now, here's the interesting thing. So when we talk about then standing waves in air column, you can look at it from 2 different perspectives. One in terms of displacement waves, right? Displacement node. The other one in terms of the pressure, right? Now the second one in terms of then the pressure. So when you're talking about then the displacement, then you get a node when it's a closed end. But when you're talking about the pressure, then there's an antinode at closed end. And in a way, what I'm going to here concentrate mostly on the displacement node. So that means, for me, when I'm talking about, for example, an air column like this, so you can see, right, it is in terms of for a pipe open at both ends. So both ends are displacement antinodes, and the natural frequencies are F equals N times V over 2L. All right, so That means this equation, which is the frequency, is exactly same as for the standing waves on a string. Okay, so you can say, right, again, you can say that lambda n is equals to, in terms of the two L over n, and then frequency n is equals to v over lambda n, and equals to, then if you rearrange, becomes n v2L, when n equals to 1, 2, 3, dot, dot, dot. Okay, so this is basically the same equation as for the standing waves on a string. So that's why, for example, then this is the first harmonic, or the fundamental, where lambda equals to L and f of 1 is equals to v over 2L. Exactly same thing. The only difference here is you get two antinodes and one node. Okay, so that means this is your n equals 1, in this case corresponding to number of nodes. Okay, that means you get basically every time where there's an open, right, let's say, and it has to be then an antinode. So, and since it's open at both ends, that means every time at both ends you have to have an antinode rather than a node. So kind of like a reverse of what we have for the standing waves. So this is n equals 2, this is n equals 3, and we basically get exactly the same thing, right? F2 is equals to 2 times F1, F3 equals 3 times F1, and so on and so forth. So in a way, other than, let's say, the shapes inside, we are basically getting pretty much same thing. For the pipe that is open at one end but closed at the other, so think a little bit different, because one thing we have here is there is a node where there is a closed end, and the antinode where is a open end, and then lambda 1 is equals to 4L, because L is equals to then quarter of the wavelength, because this is only a distance from one antinode to a node, and we know that the distance from one antinode to a node is always a quarter of a wavelength distance. And that's what we have. We have just one node and one antinode. That means in this length L, we have only quarter of the wavelength distance. Which means then in this particular case, right? So this is, lambda, in terms of lambda 1. That means, L equals lambda 1 over 4, or lambda 1 is equals to basically 4 times L. Okay, and then lambda n is equals to 4L over n. So then if I'm taking this and I'm plugging into the f of n is equals to v over lambda n, so basically what we get here is we get n v over 4L, and that's what we have over here. That means the difference here is n times v over 4L. But when we go from the first harmonic to a second harmonic, we cannot go to the second harmonic because you cannot create that type of shape inside the open closed. So that means we have to then jump to a third harmonic directly. Okay, so because one thing we do here is if I go from here to there, I'm getting to a node, and I'm not allowed to have a node because it's an open open end. That means I have to continue and until I get, let's say, basically an antinode, which then jumps into, like, let's say, shape and a half, right? That means this is then a third harmonic. So then, since I have still two nodes, so then n is equals to n is equals to 2. Okay, and then basically that's again my equation. The only thing now, n is equals to 1, 3, 5. So basically the odd numbers, right? So only the odd numbers, because again, we are, have one end is open, the other one is closed. So we have to, like, have an extra, so like, let's say, a distance displacement in order to get a node at one end and an antinode at the other end. So we end up skipping, let's say, the even numbers. So that's why it's first, third, fifth, seventh, and so on and so forth, because there's a, in terms of that. All right, so let me do this then. Before I look at this example, I want to share with the simulation here, because we can also do in terms of the, the air columns. There you go. So I can even look at in terms of these are longitudinal waves. So you can see, right? So this is basically the first harmonic if it's open and open. You can see, right? It's always, basically I'm getting antinode at the end. So in a way, if you look at it, right? So if I pause here, so basically I'm getting something like this. See, antinode and antinode. And exactly here, they have just one node. Okay. Then if I go to the second one, then this is what I get, right? So basically, again, I have to get two antinodes at the end, right? And basically a node inside. So let me see. Okay. So if I have this, so basically we're getting this pretty much. Okay. So excuse me. So this is basically for the n equals 2. Okay. Then in terms of then going from here to the next one, right? So basically then we have one extra shape. We can actually do that too, because this allows us to go all the way to the third harmonic. And you basically get something like this. Okay. All right. So then let's look at then the closed end air column. So look at the first one if it's closed end. See, this left end is a node, right? So there's a node over there. Okay. And then the wave kind of goes like this. So that means in a way what I have here is like this, right? So there's an antinode on the right side, a node on the left side. Again, so now go to the third one because there's no second one for the closed end. And then let's say the fifth one, right? So basically you get something like this. I can even show you like, see if I'm doing sort of pressure variation, so it's kind of like, let's say the opposite. See, if it's a pressure variation where there's a closed, there's an antinode, where there's an open, there's a node. The red wave light is basically for the pressure variation. So that's what we have for this. All right, so then let's go back and then look at this example here. All right, so a simple apparatus for demonstrating resonance in an air column as shown. Okay, this is actually one of the experiments that we would have done in class. This is a relatively nice experiment to verify speed of sound. So a vertical pipe open at both ends is partially submerged in water, and a tuning fork vibrating at an unknown frequency is placed near the top of the pipe. The length L of the air column can be adjusted by moving the pipe vertically. Right. So what we get here is this: the sound waves generated by the fork are reinforced when L corresponds to one of the resonance frequencies of the pipe. That means this length L, right? You can see in the picture when it represents one of those, resonance frequencies. That means the harmonics, right? For a certain pipe, the smallest value of L for which a peak occurs in the sound intensity is, let's say, 9 centimeters. So then what is the frequency of the tuning fork? Okay. All right. So that means what we're given here is that L here is 9 centimeters, which is 0.09 meters. Okay. And we know that we're talking about basically the air column, right? So this is, in terms of, if I go over there, right? So you take this fork and you hit it with the mallet, and it basically creates a sound wave, and then the sound travels and hits the water and bounces back. Okay, so basically there's air molecules kind of moving like that. That means we know that the velocity is 343 meters per second. So that's basically, we're given that. So then I can calculate then the frequency of the tuning fork as F1 is equals to then V over 4L. All right, so now why is 4L? Well, because this is closed at this end and open at the bottom, right? At the top. So this is an open close, air column basically, because the water acts like a wall. So then the sound hits the wall or the water and bounces back. That means we have F1 equals 4 over V over 4L. All right, so then 343 meters per second over then 4 times 0.09 meters, we're going to get the 953 hertz. Okay, so this is then the frequency of the tuning fork. All right, what are the values of L for the next two resonances? Now, one of the things we have for this particular, example is that, so here's, let's say that, let's say water level is right here, right? So then this is, basically you can say that if you start, this is the top. So this is water level here. So then this is our L. And if you have a, resonance, we call it resonance frequency, it means that, what you will hear is that the sound is amplified. So you know that you hit the harmonic. So then what we do for this is, remember, our tuning fork can only produce one sound, which is at the 953 hertz. Then that means the frequency is fixed. Okay. Then what we can do here is we can then change the level of the water by basically changing the L. Okay. And that can allow us to then, get the second harmonic and then change more, right? And then we get a third harmonic and things like that, because this is connected to something that we can kind of like take out the water. Okay. So we can take out the water and then we get basically different type of, resonances. For example, there's a picture that I have over here. See, like, let's say first resonance. See, this is what we get. Anti-node at the top, node at the bottom. And then the distance here for L is quarter of a wavelength. Then if I remove a little bit of water, then I'm giving enough room for the air column to go down and generate another, let's say a segment like this. And that basically gives me the, the third harmonic, right? Second resonance or the third harmonic. And if I go down even more, then I get third resonance or the fifth harmonic. Okay. So, and resonance basically means that, position of the harmonic. That means I can then find the wavelength by taking velocity over the frequency, which both are fixed, right? So then what I have here is, what I'm going to get here is 343 over 953 hertz. This is meters per second. And I'm going to get 0.36 meters. Okay, so that's my wavelength. No. So the question is right now, will then the wavelength also change when I'm changing the column, the water level? Well, the answer is no. It's not going to change simply because of this reason. Wavelength equals velocity over the frequency, and none of those quantities change. Then wavelength cannot also change. That means it's constant. But what can change is the length. So for example, for the string standing wave, we cannot change L, so we change wavelength. Here we're keeping wavelength constant. So then, and the frequency constant and the velocity constant. That means the only thing can change is the length L. And then we can calculate this, because L is equals to, remember it was n times lambda over 4, right? So it's n times lambda over 4, and basically this is in terms of our L for the first resonance. So the L for then the second resonance, or in terms of L equals 3, right? Because this is for n equals 3. This was for n equals 1. So this will be 3 times 0.360 meters divided by 4, and we're going to get 0.27 meters. Okay. Then we can have another one because it's asking for the next two. Next two will be n equals 5. Then L5 is equals to then 5 times 0.36 meters divided by then 4. So we're going to 0.45 meters. That means if we start at the bottom, let's say if we start at the top, so this distance now is about 5 centimeters from the top. Then if we go down, you can see, right, about 27 centimeters from the top. So then this is 27 centimeters. Then we're going to hit the second resonance, or the third harmonic. And if we go 45 centimeters at the from the top, then we hit basically the fifth harmonic, or the third resonance. Okay, so those are the in terms of what we get, and the relationship is this, right? L n is equals to n lambda over 4, right? Where n is equals to 1, 3, 5, like that, or odd numbers. So we can then, in a way, if we know the wavelength, we can then predict and find the resonance. All right, so the last thing we have here is what we call bit frequency. So the temporal interference which occur when the interfering waves have slightly different frequency. That means you have two waves, but a slightly different frequencies. That means, for example, one is 100, the other one is 105 or 95 or something like that. That means it's a very close, but slightly different frequencies. So then, if you're producing them together, there's this sort of like a beating, like the beat frequency, right? So the beating is the periodic variation in amplitude at the given point due to the superposition of the waves. That means think like this. So here's one wave. So, and then if the second wave kind of goes like this, it means they have basically the same wavelength, same frequency. And then when they interfere, they give me this. Okay. That means, constructive all the way, right? There's absolutely no difference between them. But let's say then what I have is then the second wavelength is slightly different. Like this. That means its wavelength is slightly less. In that case, that means it has a slower frequency. So the number of amplitude maxima 1 hertz per second is then the beat frequency, because at some point I'm going to get maximum, then minimum, and then maximum, and things like that. Okay, so that means the beat frequency is equal to the difference between the frequencies of the two sources. And human ear can detect the bit frequency up to about 20 bits per second. Okay, so basically something like this. So a little better picture. You can see, right? So you have two waves, the green and the blue in this picture A, but they are such that, for example, see a crest and a sort of crest and a trough, so they cancel each other completely. But here already you can see, right? They are not exactly on top of each other. Here, not top of each other, not at all. And then here they even have a crest and a crest, means that they're constructive interference. That means, what we get here is they destroy each other, then kind of, reinforce, and then maximum reinforcement. But then they again go until they have, crest and a crest, crest and a trough. So again, destroy each other. But then reinforce each other and then destroy each other, reinforce each other and destroy each other, because one wave has a little bit lower frequency. So for example, 100 minus 95. So then you get basically 5 hertz. That's, the beat frequency. Okay. So that's basically what we have for the beat frequency. All right, guys. So that's it for this chapter 14.